Hey guys, I welcome you all to this two-part video series in which we learn how to design spur gears. Now, in the first part, we will see how to theoretically design spur gears using various mathematical equations and check its strength for wear and in bending. And in the second part, we will see how to design spur gears in Solidworks, perform stress analysis in ANSYS, and also carry out topology optimization. Now, we'll make use of PSG Design Databook for calculating the various physical parameters of the spur gear. Now for the demonstration purposes, I have an actual model of a spur gear. This gear is of an IC engine, and it clearly shows the involute profile of the gears. Also, one thing to observe is that the teeth directions is parallel to the axis of this gear. Now, just for a bonus point of view, I also have a helical gear. Now, the differences between a spur gear and a helical gear is clearly visible. You can see that the teeth of the helical gears are inclined to the axis, whereas for spur gears they are parallel. Also, the slots that are cut into these gears is performed using topology optimization, which we will learn in the second part of this video. So before designing spur gears, let us see the types of gears that are available. Now, gears are divided into four types. One is the spur, second is helical, third is bevel, and fourth is worm. The profile for spur gears is involute. Same is for helical gears. For bevel gears, it is a conical profile. Now, the types of load that are transmitted using spur gears are radial loads. For helical gears, they are radial and thrust force. For bevel, they are radial and thrust. And in case of worm, the worm transmits radial force, whereas the wheel transmits the thrust force. There are certain factors that come into play while selecting gears. The first is the layout of shafts. Are the shafts parallel? For example, the power that is to be transmitted, that is the input shaft and the output shaft, are they parallel? Are they inclined at an angle? Are they perpendicular? It depends. The second is the input speed. Higher the input speed, higher will be the size of the gears. The third is the speed reduction. Higher the reduction, we require more number of stages and hence the complexity of the entire assembly increases. The next is cost and the last is efficiency. Now before we start designing, we need to be familiar with certain parameters. The first is the velocity ratio, it is indicated by I. I is equal to the omega, that is the revolutionary speed of the driving gear divided by the revolutionary speed of the driven gear. The next is the transmission ratio, that is denoted by I dash. Now I dash is the ratio of the first driving gear to the last driven gear. For example, if you have a two-stage reduction, the transmission ratio will be calculated from the first pinion to the last gear. The third is the pitch circle diameter. Pitch circle diameter is called D dash, or D dash equal to M into Z. What is M? M is the module and Z is the number of teeth. The next is gear ratio. Gear ratio can also be called velocity ratio. That is, the N is denoted by the revolutionary speed, that is that of pinion divided by that of gear, or this is also equal to the number of teeth of gear divided by the number of teeth of pinion. The C to C, that is the center to center distance, is denoted by A. Now A is given as half ZP plus ZG into M. Now let us look into a problem. The problem states that a power transmission of 8 kW is desired between the input shaft and the output shaft. It is given that the input shaft speed is 960 rpm and the output shaft speed is 48 rpm. The shafting condition is parallel, type of system is a closed gearbox, and the number of stages are 2. Now we need to decide the reduction pair and also design the low torque pair. Low torque pair is basically the pair which has the highest reduction. Let us look into the steps that we will follow for designing the gear pair. The first is we need to find the reduction per stage. Second is illustrate a rough layout based upon the type of stage that we are selecting. The next is selection of motor. This factor will depend on what amount of power that we require and what is the RPM. The next is finding the number of teeth for the gear pair, that is for pinion and for gear. Next is selecting a specific gear material. After that, we need to find the weakest element and perform the design calculation on the weakest element, since there is no point in designing an element that is already strong. So we need to find the parameters for the weakest element and design it accordingly. And after the designing process is done, we need to check whether it is safe for wear and is it safe for dynamic load. Now it is given that I overall, that is the transmission ratio, it is equal to the input speed divided by the output speed. So as you have seen previously that the input speed is 960 rpm and the output speed is 48 rpm. This accounts to 20. Now since we are selecting a two-stage gearbox, I per stage will be equal to root of 20. Had it been a three-stage gearbox, this would have been cube root of 20. Now this value comes out to be around 4.47. Now for the ease of calculation, we will say that this reduction is 4 and the other reduction, that is, let's say this is the first stage, and for the second stage we will take it as 5. Now a thing to note is that the multiplication of both the reduction should be equal to the I overall. Hence we have not violated any type of law. Now in order to control the overall size, what we do is we consider a low torque pair first, that is a high reduction. So let us say that I1 is equal to 5 and I2 is equal to 4. Note that I overall is equal to I1 into I2. The next step is to design the layout. So let us say that this is the first stage and this is the gear for the first stage. There is an intermediate shaft and this is connected to the second pinion, and the pinion has its gear of the second stage, and this is the output shaft. So let's say this is the input and this one is the output. This will form a rough design for our gearbox layout. So from here to here, this is the first stage, and from here to here, this is the second stage. Now the next thing is to select the motor. The power requirement at the output is 8 kilowatts and the number of stages are 2. Note that for Spur gear, efficiency per stage is 98%. So we need a motor that gives a power output of more than 8 kilowatt, such that after we compensate for the efficiency loss, the output power is 8 kilowatts. Hence the motor power will be 8 divided by 0.98 into 0.98. Since we have two stages, this comes out to be 8.33 kilowatts. So we select a design power of 8.5 kilowatts, as this kilowatt rating motor is easily available in the market. Now the tool profile that we will select will be involute profile with a pressure angle of 20 degree, full depth and no correction. Now there is a criteria for having a minimum number of teeth on pinion. The formula is given by Z minimum equal to 2 upon sine square alpha, where alpha is the pressure angle. So when we substitute the value of alpha as 20, what we get is the minimum number of teeth, let's say Z minimum, should be greater than 17. This is a rule. So for our purpose, let us take Z1 is equal to 18. Right? Now using the formula for velocity ratio or the gear ratio, We can find the number of teeth on gear. This is the number of teeth for pinion. So Z2 will be equal to I into Z1, or let's say I1. Now I1 is 5. 5 into 18. This comes out to be 90. There is another phenomenon in gear designing known as hunting. I'll include a link somewhere towards the top right of this video to explain what is hunting of tooth. In the case of hunting, we take one additional tooth in order to prevent the wear on the same tooth after one revolution is completed. So we will take Z2 equal to 91. Now we need to find the exact gear ratio. This is equal to Z2 by Z1, and this comes out to be 91 divided by 18, and this is around 5.056. In our further calculations, we will use this value and not 5. The next task is to select the material. We can select the same material, but for our case, we will take C50 for our pinion. Sigma ultimate is 720 megapascals. Sigma yield is 380 megapascals. And the value for brittle hardness is 241 HB. And we select C35 for our gear, specifications of which are given here. So the ultimate strength is 570 megapascal. The yield strength is 310 megapascal, and the brittle hardness number is 187. So the first task on our hand is to check which element is weaker. So whether is the pinion weaker or is the gear weaker. Generally, it is a notion that the pinion should be the weakest element and we have to design the pinion first, and accordingly we have to find the value for module and the number of teeth for the gear. So there is one way to check that using a Lewis form factor. The formula for which is given in the PSG Databook on page number 8.50. So we are in the PSG Databook of page number 8.50, and here the Lewis form factor for 20-degree inverted profile is given. That is y equal to pi into small y, and this is equal to pi into 0.154 minus 0.912 upon z. Now in order to find the Lewis form factor of the pinion, we just have to replace z for that of pinion. So let us say I am calculating it for pinion, so y1 will be corresponding z1. Now z1 is 18, so let us substitute it in here. This is 0.154 minus 0.912 divided by 80. You put this value in a calculator and the answer that you get is 0.324. Similarly, for the gear, that is y2, the value for Lewis form factor comes out to be 0.452. Remember that for gear we have to substitute the value of Z as 91 and not 90 because of hunting, as explained previously. Now in order to find the weakest element, what we need to do is we need to calculate this product for pinion and for gear separately. It is sigma y for the pinion material into the Lewis form factor for the pinion, so that is y1, and the sigma y for the gear material and y2, and we have to check which one is greater. If we calculate this value, this comes out to be 380 into 0.324, which is 123.35, and for the gear material, let's say 310 into 0.452, and this value comes out to be 140.2. This value is bigger. That means the pinion is the weakest element, just what we wanted. So now we need to design pinion first based upon the various theories and the formulas as indicated in the PSG Databook. So let us write this note that we will design now. This modified Lewis equation is given on PSG Databook, page number 8.13a. Yes, this is that formula. This is the first one. I'll write this formula on this page. That is the m, which is our module, should be greater than 1.26 times the cube root of the design torque. So remember, whenever any symbol has a square bracket around it, it is the design value and not the actual value, divided by the Lewis form factor sigma b, that is the bending strength, into psi m, this is a constant, and the z, that is the number of teeth. So we'll take this formula in part by part and we will find the values for each individual element. So let us start with the design torque. Now how do you find the design torque? We have this formula that torque equal to power upon omega. So let's say that this mt is equal to P upon omega. Now the power that we had selected was 8.5 kilowatts. So it is 8.5 into 10 raised to 3. And omega is 2 pi n divided by 60. This is revolutions per minute and this is radians per second. So when we substitute the value of n, what is the value of n? The value of n is 960 rpm. So you substitute the value 960 rpm here, and what you get is 84.5 Newton meters. Now you go to PSG Design Databook, page number 8.15 here. So we have this formula to calculate the design torque. The design torque is the MT, that is the actual torque, into kd into k. Now this is a constant value. Now for psi value of 10, we select kd into k as 1.3. Right, the first one. Initially assume for symmetric scheme, the value of kd into k is 1.3. So we will write here that the value for design torque is equal to mt into kd into k. The value of kd into k for our case is 1.3 and the value for mt is 84.5 Newton meters. Now substitute the value for mt and kd into k here, and what we get is the value of design torque comes out to be 110 Newton meters. So the first term is done. Now we already have the Lewis form factor. Now since we are designing it for a pinion, I can easily write it right here as 1. The second task is to calculate the bending strength, the design bending strength. Now to calculate the design bending strength, we need to go to PSG 8.18. They have given the formula to calculate the design bending stress. So this is the design bending stress. I'll write this equation here. So sigma p square brackets, mind it, is equal to kb into L divided by n into k sigma times sigma naught. Sigma naught is equal to 1.4 times sigma endurance. KBL is the life factor. We will find it using the table 22, which is given in the PSG Databook. K sigma is the Phillips stress concentration factor, which we will also find in the table 21. The sigma minus 1 is endurance limit, and n is the factor of safety. When we turn our page to find the table number 22, 21 and 20. Now to calculate the value factor of safety, we are considering the steel, which is a cast iron, and a tempered or a normalized steel. So in our application, we have a factor of safety of 2. So the first term is 2. That is the value of n is 2. Let us calculate the value of sigma naught. Oh, sorry. First, I'll write the formula for sigma naught. Sigma naught is equal to 1.4 times sigma endurance. Now, how do you find the sigma endurance? You come here to page number 8.19, and the first column that you see is the formula to calculate the sigma endurance. Since we have cast steel, the value of sigma endurance will be 0.22 times the ultimate strength plus the yield strength. Now this product multiplied by 0.22 and plus 500. So this is the value of sigma endurance. So 0.22 times sigma u plus sigma y plus 500. So we have this done. So now since we know sigma endurance, we can calculate sigma naught. So sigma naught is done, n is done. Now we have to find the K sigma value. K sigma value is the fillet stress concentration factor. Now since our steel is normalized and it is surface hardened, we will select the value for K sigma as 1.5. So here we write as K sigma equal to 1.5. Now we have to find KBL. For steel material, our value for sigma, our value for the surface hardness for the pinion material was 241, which is less than 350, and the number of cycles is greater than 10 raised to 7. So the value of KBL will be 1. Let us write it here. Value of KBL equal to 1. Now we know all the value for in order to find the design bending stress. So we know sigma u, sigma y, we have the KBL, we have K sigma, we have the value for n, we have the value for sigma naught. Just put all these values into this equation, and what we get is the value of sigma b as 136.3 megapascals. So in the modified use also, I forgot to tell you one thing, that the value of sigma psi m is 10. This is a constant value. So now in this formula we have the design torque, we have the Lewis form factor, we have design bending stress, we have the value of psi m, and we have the value for the number of teeth on the pinion. You just plug all these values into this equation, and what you get is m should be greater than 1.26 times cube root of 110 into 10 raised to 3, since it is kilowatt rating, 0.324 into 136.3 into 18 into 10, which comes out to be m should be greater than 3.02. Now for safety purposes, what we take is, we take 30% more module than the calculated one. So we multiply this by 1.3. So what we finally get is m equal to 1.3 times m dash. Let us call this m dash, and this is equal to 1.3 into 3.02, which is equal to 3.9. Now according to PSG Databook, page number 8.2, table 1, there are a set of values of m that we can take. So the closest one possible is the value 5. So for our purposes, let us take the module as 5. This is the final module. Now the design is done. Basically we have the module of gears, we have the number of teeth. So now we can design a gear. But the thing is, we need to check whether it is safe or not. So is the value of module, is it safe for our application? Do we need to increase the value of module? Do we need to increase the number of teeth? For checking purposes, we will check the gear for wear. So let us name this that checking the gear, or let's say the pinion for wear. Wear In gears, the wear is caused due to the compressive loads between the pinion and a gear. So this can also be called as the compressive wear check. Let us go to PSG Databook 8.13. Here it is. So the value for sigma c. So we have done with the designing. Now we need to check. The value for sigma c for spur gears is this formula. Sigma c 0.74 I plus 1 upon a root of I plus 1 upon I into b times E into the design torque. Now you all be guessing what is the value of A, what is the value of B, and what is the value of E. The A is the center to center distance between the two shafts. B is the face width of the gear. The value of E is the Young's modulus. The I is the reduction, that is for our case we are taking it as phi, and this is called the design torque, which you already know. So for calculation purposes, we will take the value of I exact, which we have calculated as 5.05. Now A is called the C to C distance, and the formula of which is already discussed before. So this is 1 by 2 into Z1 plus Z2 multiplied by M. Now this is the 1 by 2. Z1 as we know as it is 18. Now Z2 is 91. The module is 5. This value comes out to be 272.5 millimeters. That means the shaft which will carry our pinion is at a distance of 272.5 millimeters from the shaft which is carrying our pinion. The B thing is called the face width, the formula for which is given as M into psi m. Now we know the value of m, and psi m is a constant as we all know. So it is 5 into 10, and this comes out to be 50 mm. The design torque, which you already know, I'll write it again. Here it is 110 into 10 raised to 3 Newton millimeters. Alright. So, and the value for the Young's modulus for steel is given as 2 into 10 raised to 5 Newton per millimeter square, or you can also call it as megapascal. So we know all the parameters that are required to calculate the value of sigma c. So now we just need to plug in these values into this formula. I'll write as sigma c. Upon calculations, we get C sigma c induced. The induced basically the compressive stress that is going to act on the gear. And one way to check is we need to find the compressive stress that the gear is able to handle. So if the sigma c that is induced is less than the sigma c that it can handle, we can say that our gear is safe in compressive wear. So I'll call the sigma c induced. This value is equal to 377.2 Newton per millimeter square. Right? Now in order to find the sigma c that the gear can resist, we go to PSG Databook 8.16. So this is 8.16 PSG Databook, and the formula to find the design surface or the contact compressive stress is given here. So it is CB into HB into KCL. This is kgf per centimeter square. So I'll write the formula here. This is sigma c is equal to CB. Now note that this square brackets means the design compressive stress, and this thing is the induced compressive stress. CB into HB to KCL. Now the value for KCL, you can find it here. It is a life factor, and you can find it from table number 17. As you know that value of KCL is 1, but inner hardness value is 241. The value of CB is 25. I'll show you how. Here they have given for carbon steel and alloy steel. Since we have C35 as our as the material for pinion, we are taking it as carbon steel. The heat treatment that we are going to do is normalizing, harden and tempering. And we have the value of HB as 241, which is obviously less than 350. So we can easily take or safely take the value of CB as 25. So we know all the three terms. Now just put in these values and find the design compressive stress. This comes out to be 25 to 241 to 1, which is 6025. And mind that this is kg per centimeter square. When we convert this thing into Newton per millimeter square, we get it as 602.5 Newton per millimeter square. So now, one thing to note that sigma C design is greater than sigma C induced. What do we understand by this? That the value of compressive stress that we are exerting on the gear and the value of compressive stress that the gear is able to handle is well within the safety limits. That is, the gear is able to handle more stress than what we are inducing, and hence we can safely assume, or rather we can safely predict that the design is safe in compressive. So now that the compressive check is done, we need to check whether the gear is safe for dynamic loading or not. There is a formula to find the static force that is going to act on the gear, which is given as Fs equal to the design bending stress into the face width times module into the Lewis form factor. Now Yp, because the P indicates pinion, we have the values for each and every term. We have the design bending stress as 136.3. We have the value of face width as 50 mm. The value for module is 5 mm, and the Lewis form factor for pinion is 0.324. After calculations, we get this value as 11 kilonewtons. Now, what we need to do is, we need to find the dynamic load, and if the dynamic load is less than the static load, we can safely assume that our gear will be safe in under dynamic loads. So now how do we find the value for dynamic load? The value, in order to calculate dynamic load, we go to PSG Databook, page number 8.51. Just a correction, we need to go to PSG 8.50, and here it is given that Ft, that is the dynamic force, equal to Ft into Cv. Ft is the tangential force. Now tangential force is calculated using the design torque. So I'll write the formula as Ft is equal to Ft into Cv. Now we'll find the value of Ft in Cv after this. The value of Ft, as we know that torque is basically force into distance. Now in our case it is the radius of the gear, and the design torque is the torque that is driving that gear. So in order to find the tangential force, what we do is we divide the torque by the radius. Now we don't know what radius is, but we do know what is the diameter, and the diameter is called the pit circle diameter. We know the formula D equal to m into z. So in order to find the radius, we need to divide the diameter by 2. This will be mz by 2. So let's write it here as mz by 2. The value for design torque, as we all know, is 110 Newton meter. So in order to do it Newton millimeter, what we do is we multiply it by 1000. The value for module is 5 mm. The number of teeth is 18 and divided by 2. The value that we get is 244.4 kgf. Note the units. It is not the force in newtons, rather it is the force in kilogram force. Now when we go to PSG 8.51, this is the formula to find the value for Cv, where V here Vm is the mean velocity. So in order to calculate the mean velocity, what we need to do is we need to convert the rotational force into a unit for meter per second. So the value of Vm equal to pi t into n, right? but we have it in meter per second, and the revolutions is in revolutions per minute. So we divide it by 60. This comes out to be pi. Now d, as we discussed, is m into z, so it will be m1 into z1. Let's say m1 into z1, and this is n1, and we divide it by 60. So the formula, the value for Vm that we get after substituting all these values is 4.53 meter per second. We come to PSG 8.51. We write the formula for Cv as Cv equal to 3 plus Vm divided by 3. This is from PSG 8.51, and this is equal to 3 plus 4.53 divided by 3, which is 2.51 meter per second. So now I rewrite the formula to find the dynamic force, which is equal to Ft into Cv. We have the value for Ft and also the value for Cv. So substitute this in this equation, and this comes out to be 244.4 into 2.51, which equals 613.44 kgf. Right, this is the dynamic force. Now the static force Fs was 11 into 10 raised to 3 newtons, which when converted in kgf comes out to be 1100 kgf. So we note here that Fs is greater than Ft, which means that the static force that the gear can carry is greater than the force, the dynamic force that is going to act on the gear. And hence we can write a statement
that the design is safe for dynamic loads.
There is another way to find the dynamic load using the Buckingham's dynamic load. Now for that we need to go to PSG Databook 8.51 to find the formula for Buckingham's dynamic load. The value for Ft, that is the dynamic force, is tangential force plus this whole bracket. Now for C we need to refer table 41. So let me just first write the formula for Buckingham's dynamic load. We have the value for Vm. We don't have the value of C, we'll find it using the table. We have the value of B, that is the face width. We have the tangential force component. We just need to find the value of C. Table number 41 is on the next page. This is the value of C. Now we have selected 20-degree full depth, and the material of pinion to gear, both of them are steel. So we'll select steel to steel, which is equal to 11860 times E. Now E is the expected error. Expected error we can calculate from this table. Now we have a module of phi. So the expected error. So many times precision gears are not possible. So what we do is we take it as first class commercial gears. These are easy to manufacture and hence they are widely used. Our module is phi. The value of the E value will be 0.056. So I take it as 0.056, and what I get is 11860 into 0.056. This value of C is 664.16. Now this we'll use this value to find the Ft, that is using Buckingham's dynamic load. I'll input all the values. So this is 244.4 plus in the bracket the 0.164. We have the value of Vm as 4.53, and since it is a meter per second, we need to find meter per minute. So in order to do that, what I do is I multiply it by 60. Right? Now the value of C is 664.16 into the value of B, that is the face width. Face width value
is 50 mm, and we add this by 244.4. The denominator side we have 0.164 times 453 into 60. This is meter per minute, and the value of Vm that we calculated, that is 4.53, is meter per second, plus 1.485 times square root of 664.16 into 50 plus 244.4.
The value of FT comes out to be 564.4 kg of force. Here too, the value of Fs, that was 1100 kgf, Fs is greater than Ft, and hence I can state
that the design is safe under Buckingham's dynamic load.
So this pretty much sums up the theoretical calculations which is required to design the gears. In the next video, we will see how to design this gear in Solidworks and perform stress analysis in ANSYS and also perform topology optimization. Thank you for watching.